This is the lecture number 4 of the course AU 203 Statistics and Quality Control. In this lecture, we will talk about the measure of the central tendency of the data, and we will go into arithmetic mean and the median, mode, and we will compare the common measures of central tendency, these mean, median, and mode. And then we will go into the concept of trimmed mean and weighted mean, and in the end we will look all these things in Minitab as well. So measures of central tendency is means the data that represent the bulk characteristic of the data. So what value, what guess value which is actually representing the bulk of the data is termed as a measure of central tendency, or sometimes it is called as the measure of the location. Where the mean is actually lying, and mean is the term which is actually whenever we use, most of the time we mean arithmetic mean, but mean could be a geometric mean, it could be a harmonic mean. So mean is one of the measure of the central tendency of the data. And arithmetic mean is one of them. Median is another measure of central tendency. Mode is another measure of central tendency. And sometimes we need to work out a mean which is called as a trimmed mean. We need to get rid of the extreme values, and in group data or in the frequency data we need to work out the mean. Sometimes it is called as weighted mean. So what mean is actually, mean is when you say an average is actually representing any of the measure of the central tendency. So average could be a mean, average could be a median, average could be a mode, so which represents where the most of the data is actually lying. So for example, in this histogram, the data X starts from 0 to 70, and the from 40 to 50 is lying over 20 is the frequency. So most of the data is lying from 30 to 60, where the most of the area of this curve, area of this histogram is representing. So your measure of central tendency would be lying between 30 to 60, whether it is a mean, whether it is a median, or whether it is a mode. So in trimmed mean we are ignoring the AND values, and in weighted mean we will take into an account the effect of the frequency and the data. We will see it in the later part of this lecture. So this average is actually a single word which can be used to signify the central tendency of the data, where the most of the data is lying actually. How to calculate the mean? You know, if you have a sample and have n observations, so the first observation is x1, second is x2, third is x3, and so on. Xn is the nth observation. So what we need is to calculate the sample mean is take the sum of all the n observations and divide it by the number of observations. So your number of observations is n, then this would be representing the mean of the data, and sum of the observations can be written in this shorter notation called sigma notation, where I is a subscript. So if I is 1, then it will be x1, if I is 2, then it will be x2, and sigma is denoting that these x1 x2 are summed up together. So the neater way of writing down is actually the sigma notation. So x bar is actually sum of x divided by n, and keep in mind the notation of the mean, calculating the mean, because x1 x2 are the observations and n is the total number of an observation. Since it's a sample, so it would be called as sample size. Small n is representing the sample size, and we use letter bar over x, we use a bar to represent the sample mean. If your observation is taken from your population, so we are investigating not just simple so here actually it should be not small n, it should be capital N actually. So your all the observations is something going from small to capital N. So your population mean is actually the sum of all the observations, and here we are not taking the sample, but we are taking the sum of all the observations in a population. So, and the symbol for representing, usually we use the Greek letter to represent the population parameters. So population mean is represented by letter mu, a Greek letter, and capital N represents the total number of an observation. So this total number of observations, capital N, differs from population number of elements, number of data set present in the population, the whole population. So population mean would be the sum of all the observations from 1 to capital N, and divided by N, that would be able to calculate the population mean. Okay, let's say we have a problem in which you have a random sample of 10 observations of piston ring diameters which are in millimeter, and the values noted for these 10 observations is some observations like 52.3, 51.9 and so on. So this is a random sample. So we have the population, and out of that population we have picked a sample of 10 observations. So we have to apply this formula for calculating the mean. Here it is just mentioned mean, but here the mean to be calculated is from the sample. So from the given statement, one need to find out whether it is a sample mean or a population mean. So here it is a sample mean, and what you need is to take the sum of x, sum of all the observations. There are 10 observations, and divide by 10, so you will be able to calculate. So keep in mind this 52.3 millimeter is actually the average diameter of a piston ring. So this is the arithmetic mean, because we have taken the sum and divided by n. So that is actually the arithmetic mean we have worked out for a sample. There is another problem in which, let's say there is an engineer is designing a nylon connector, and engineer is considering establishing the design specification on wall thickness at 3 by 32 inch. The connector wall thickness is 3 by 32 part of an inch, but engineer is somewhat uncertain about the effect of the decision on the connector pull force. So this connector is something like connecting one wire to another. So in order to open it, you need to apply a force, and we call here as a pull force. So if the pull force is too low, the connector may fail when it is installed in a device. So each prototype units are produced, 8 prototype units are produced, and their pull-off forces are measured, resulting in the following data. So only not the whole batch is produced, only 8 prototype nylon connector has been produced, manufactured, and their pull-off force is measured in pounds. So it could be 12.6 pound pull-off force, so 13.4 and 12.3 and 13.6. So first thing is to visualize the data by drawing a dot plot. So once you draw a dot plot, so you will be able to see the distribution of your observation. So some observations close to smaller than 12.4, and some are 13.6. So the data is well distributed, where the thickness of the nylon connector is 3 by 32 inch, the thickness of wall thickness of the connector. So there are some different ways of visualizing the data. You can plot the individual value plot, you can do the histogram, you can do the dot plot. We have already learned there are several ways of visualizing the data. Even though the second part is to calculate the mean of the data. So what will be the one representative value of the pull force instead of 8 different values? So what we need is, we need to calculate the arithmetic mean, and here I have calculated the arithmetic mean by taking the sum of the values, first value x1, then second value is x2, and I took the sum, and the sum comes up 104 and divide by 8. So 13.0 pound is actually the mean force, and keep in mind this mean value is not actually present in the data. So it is not the observation you have made, but it is actually some representative value which is actually coming into the center. We call that to be, that value to be the central tendency of the data, where the location of the center point can be worked out. So mean is actually representing the location of the center point. So here the center point lies at 13.0 pounds of force. Okay, so but what you see here is this average force is measured, but from testing these prototypes, 8 prototypes, engineer note that the average pull-off force is 13 pounds. So this is something you got it from the value of mean. However, engineer thinks that this may be too low for the intended application, so he decided to consider an alternative design with a thicker wall of 1/8 of an inch in thickness, and 8 prototypes of this design are built. So he has developed nylon connector with the thickness of a much wider, thicker wall, that is 1/8 inch, and each prototype of the design is built and observed, measurement is taken, and the measurements are 12.9, 13.7, 12.8 and 13.9. So obviously we need to look into how these the two different measurements, one is 3/32 inch and how 1/8 inch is distributed. So we need to do a dot plot, combined dot plot of these two observations. So here the colored circle is representing the 3/32 inch, and without a color, this circle is representing 1/8 of an inch. So what we notice from that is the higher average higher pull-off force is required in 1/8 of an inch, which might perform its intended function, whereas with the smaller thickness the mean is different. So mean here is different. 13 pound force is for the thicker wall, for less thicker wall, and 3/32 inch, and for 1/8 inch. So we calculate the average for this data, and this data comes out to be 13.4 pounds. So some higher force, average force is needed once your nylon connector is of thicker wall. So what we notice here is increasing the wall thickness actually has an impact on the pull-off force or the strength of the connector. So once you need a more pull-off force, it means the connector is doing its intended function, and it is connected, and it is not going to be removed easily. So by increasing the wall thickness, we will be able to increase the average pull-off force by a magnitude of 0.4 pounds increase, by increasing the thickness of the wall connector from 3/32 inch to 1/8 inch. So from this example you learned that okay, but making the wall thicker, you need to put more material and more cost, but at the same time your the function of your connector has improved, because the average pull-off force becomes higher, so that the connector is not going to detach so easily, and it would be a better product in the end. Okay, so the next measure is called median. Median is actually the middle value of the data, which actually divides the whole set of data into two halves, and the median is actually representing the middle value. So the life is simple. If your observation is odd number of an observation, let's say you have 5 observations, so 1, 2 is the end values, and 4 and 5 are another end values, so 3 would be your median in that case. once your data is odd. So life is simple. Once your data is odd, let's say for example with the same measurement of the diameter of the piston ring we have taken in the beginning, let's say you have 1 2 3 4 5 6 7 8 9 observations. So if you have odd number of an observation, the first step is to arrange the data in the order. For example, minimum value is here 51.9, and then 52, then 52.1. So it is actually arranged in an increasing order. And median is because is the middle value, but from an ordered list, whether it is in ascending order or descending order. Even if you put in a descending order the biggest number 52.6 first and then the smallest on the other side, it won't make any difference on the middle value. So your data is in order, so you need to get rid of these extreme values. So you get rid of these 1 2 3 4 values on this side, 4 values on this side. So the middle value is 52.3, which will be called as the median of the data. So if you have n observations, which is n is an odd number, then the n plus 1 upon 2, it means fifth observation would be your median. So these are 4 observations, so fifth observation would be your median, and you can write, if you have number of observation n and n is odd, then the median would be lying at a position of n plus 1 upon 2, which will be the fifth position in this data. Okay, the things would be different if your number of observations is even, and the median would be actually, there will be not one median, but it will be the two middle values. So what you need is to take the mean of these two middle values. That would represent the median. So for example, here you have 10 observations, and what you need is the next step is to bring obviously the data into an order. So 4 observations here and 4 observations here. So now you have 2 observations in the middle. What you need is to take the average of that 2 values. So 52.35 in this case would be the median of data, which is representing the middle value. So if you change the order, for example, instead of ascending order, if it is descending order, then these 4 would come here and these 4 would come here, and middle value would remain these 2 values. So median would remain the same. So that's why it is written as ascending or descending order. So here what you need is the fifth and the sixth values. If it is a 10 values, let's say an even number, then the fifth and sixth value you take the mean. So if your number of observations is even, then the median is the mean value at the position fifth position and sixth position. So that would be, if you these two positions, if you take the mean, it will be the median of your data set. So what actually median is doing, median is dividing the whole set of data into 2 halves. So median is actually middle value of the data, which is divide the whole data set into 2 parts. So if you draw a line here, half of the data on the other side and half of the data would be on the other side. So that is what median is. So median doesn't been affected if you change the extreme these end values, because these end values are not being used in the calculation of the median. So because you median is actually the middle of the data. So from the bringing change in the extreme values does not affect onto the median. So this is one of the advantage of the median. Okay, mode is actually called the most frequently occurring value in your data set. So for example, if this is your data set and you see 52.3 is coming one time, second time, and there are 3 observations in this data set which are actually coming frequently. So 52.3 would be called as a mode of this data set. So mode is actually the most frequent value which is coming in the data set. That would is representing how most of several if more values are there, it could be 5 values, it could be 2 values. So whatever the number is, then it would be called as mode. But if there is every data is unique, then there will be no mode at all in the data. So there is a possibility that the mode is not present in the data if the numbers are not repeating. For example, in this case you have data is 52.3 is one data which is twice, and then 52.4 and 52.4. So this data set has two modes. So it would be your bimodal distribution having two modes. 52.3 is a mode which is coming frequently and 52.4 is coming frequently. So we call that data has two modes. If your data distribution is a single mode, so mode would be in the middle value, and that is actually coming into the center, measure of central tendency, and that is the highest number of occurrings for that particular x. For example, on the horizontal axis you have some x and the frequency is placed on the y-axis, so that particular value is having highest frequency. So that would be your mode of your data. So since there is a one mode, you call it a unimodal distribution. If your distribution looks like this, it means for this value occurring is this, and for this value the occurring is this. So it has not one mode but it has two mode. So such a distribution is called bimodal distribution. If your distribution is uniform just like this, it means within the range of values, all values are exactly the same. So there is nothing is being repeated. So in this way we call this has no mode at all. So there is no mode is not present in that data set because the distribution is uniform. Okay, so in this problem you have some data set, and first thing is always visualizing the data. So this you need to keep in mind whether you are calculating whatever statistical parameters you are calculating. The first thing is to visualize the data, and then you need to look into the measure of central tendency or measure of dispersion, what you will we will learn later, but we need to visualize the data first. So here we make it a dot plot of the data, or we could have an individual value plot. So you see the minimum value is less than 2 and the maximum value is 14, and we don't know what is the middle value, but we will calculate the value like adding all the observation. Then 6.5 is the value which is not present in our observation, but this is actually representing the mean of the arithmetic mean of the data. And then we have to arrange the data in the order, the smallest value, let's say 1.4 first, then 3.9, and then 5, and all that. And then we need to calculate the median because it is even number of an observation. So we get rid of 2 here, we get rid of 2 here. 5 and 6.2 are the two middle values. So we take the mean of these middle values, and if x is your observation and we use the symbol x tilde to represent mean, right now I have not shown here, but x and some notation of tilde is used on top of letter x to represent the median of your observation. So if we need to calculate the mode, so there is no mode present because there is no data which is repeating it. There is no repeating data, then the mode doesn't exist in that data set. Okay, suppose we have the sample that has increased some value, let's say 26.1. Some value is increased, so your data set is some 26.1, I mean has increased. So here it is actually 26.1. Okay, so I have that data set and okay, some data has changed. So what you see is just by adding one value, our distribution of the data has changed. So our maximum value has been crossing over 24, that is 26.1. So this is something not actually part of this population or this data set. So this number is a bit different from this data set, and we might call it the data set to be something in outlier, which is not representing this data set because its middle value is 5.6 and its mean is 6.5, but due to that number, this number is far away from the this location of that number is far away from the location of the mean value. And from Minitab we will see, once we have calculated the descriptive statistics, we can see the mean value in that case has changed from 6.5, now the mean value is 8.5, and minimum value is 1.4 and its maximum value is 26.1, and its middle value is, and you can see here just bringing the extreme value, the mean has changed from 6.5 to 8.5, but your median value remains the same. So because the middle value is not being affected by the extreme value, so this is an advantage of calculating the median. Okay, so mean, median, mode, and if we have to compare our data points, so just think of all these data points are some masses, and what you need is you need to place a fulcrum so that this weight are balanced together. For example, it is 26.1 kilogram, it is something 1.4 kilogram, and so on. Let's say all these dots represent masses. Then what I need is I need to place a fulcrum so that it balances out, and that point would be your arithmetic mean. So arithmetic mean would be balancing all that data to that point. So that would be the balance point where all the data is centralized, or where you can put your fulcrum so that all these weights are balanced with each other. And you know from your mechanics, there would be the forces acting downward and creating a torque in this anti-clockwise direction, and this is creating a torque in clockwise direction. So it is a 26.1 kg and lot of distance. So all the sum of the torque in anti-clockwise and some of the torque would be clockwise would balance out so that it would be in equilibrium. So this is the feature of the mean. Whereas if you put your fulcrum on the median point, which is 5.6 in the data, or with the 26.1 observations, then your fulcrum is not going to balance. So even though the middle value is actually representing that half of the data set is on this side, half of the data is on this side, but it is not actually balancing the weight. So mean is actually your center of the gravity actually, where whole of the weight is being lying, whereas median is dividing the data set into two halves. So 3 come here on this part, 3 come on this part, but it won't balance that fulcrum. Okay, so if you look closely, the average, the comparison of the mean and median, mean is something where you don't need to sort your data. This is a good point about mean. Your sorting is not required, or ordering of the data is not required. And all of your data points are used in your estimation of the central tendency. So that is what is required in the mean. And since you are summing up, you are using the mathematical operation, adding them together and divide. So obviously the scale of measurement should be the ratio, because you are adding them as well as you are dividing them. So it means it has all the mathematical basis is present in the mean. So it is mathematically somewhat easier to calculate. The disadvantages of the mean is, for example, we will see in the MATLAB, in the Minitab as well, this if your data has some extreme values, some end values, and if you put 26.1, then you can see that your mean has changed from 5.6 to 5.8 in the previous data set, so which is one of the disadvantage. And you see that actual value of the observation is actually not a part of your data. That is also can be considered as a disadvantage. And since it's a mathematically you need to add them, because it's not a 10 observation, if it's a large number of observation, then compared with the mode and median, it is more time consuming. Okay, whereas in median actually you need no mathematics, you don't need any calculation, and we have learned that median, at one of the biggest advantage of median is it is unaffected by the extreme values. Disadvantage is you need to first order your data, sort your data, whether in ascending order or descending order, and then you can look for extreme values. No? So sometimes we can overlook the extreme values which could be useful, which are part of some observation, might be due to some error or something that can be overlooked once we are calculating median. More variation between the samples. So from sample to sample, different data set would have different medians. A mode is the most frequent data which doesn't require any calculation, so we just need to look which data is occurring most. That would be your media mode, and obviously you don't need to sort your data, and since it's the most repeating, so whatever your smallest values or the largest values, it doesn't affect on that. And even if your data set is placed, so you can visually determine the mode. And disadvantage is some data do not have mode, or some data do have bimodal, trimodal or multimodal distribution. Okay, so then concept of trimmed mean comes. For example, trimmed mean, we don't take into an account the whole data set of an observation. What we do is by keeping certain percentage, we do not include all the data points, but we delete some of the data points which are very low or some which are very high. In this way, we'll be able to calculate the mean. So mean, the disadvantage of the mean can be taken care in this trimmed mean. For example, if we have to compute 10% of the trimmed mean, so what we do is for the whole data set, let's say if your data set is 100 observations, then 10% lowest and 10% highest on both extreme values are ignored. So only 80% of the data or 80 observation is taken into an account while calculating the mean. For example, if you have this data set and you have to compute the 10% trimmed mean of this data set, so first you need to calculate how many, first you need to arrange things in an order. So lowest values are these and the maximum values are these, and your 10% here is 20. There are 20 observations here, so 10% of 20 would be 2. So 8 and 10 and 40 and 50 to be considered as to be trimmed from that data set. So we trimmed 8 and 10 and 40 and 50. Now our data set is comprising of only 16 observations. And if I use Minitab to calculate the mean of the 16 observations, I end up with a mean which is 19.813. So which is far away from the minimum value as well as from the maximum value. So that is actually the concept of the trimmed mean. If we another way, sometimes the data is grouped into different groups. Like for example, in a survey at a particular point, you are observing how many cars are passing in a 5-minute period. So 0 to 9 number of cars were passed 5 times in your observations. 10 to 90 number of cars passed 8 times, and 20 to 29 cars were passed in 13 times. So you just group that data, and what you need is number of cars, the average number of cars or mean number of cars that has to be passed. That is something we have to work out. So what we do is, since this data is in the have some lower limit and upper limit, or sometimes they call is interval data. So in that interval data, the data lies between 0 number of cars to 9 number of cars. So what we do is 0 plus 9 divided by 2, we take the middle value of the class interval. So middle value would be 4.5 and its frequency is 5. So we calculated all the middle values, 10 and 19. So take the average of 10 and 19, that would be your 14.5, that would be the mid value. So this is your mid in that histogram we have seen that there is a bin, and in that bin there is a cut point, and cut point ranges from 10 to 19. So middle value is midpoint would be between 10 and 19, that would be 14.5. So you have the same frequency. So what you need is to make it a table like this, midpoint multiplied by the frequency, and here for example 4.5 multiplied by 5, you get 22.5. So you take the sum of all the frequencies, sum of all product of the midpoint and the frequencies, and take the sum and divide by the sum of the frequency to calculate the average. So here average of that x number of cars would be sum of f of x divided by sum of frequencies. Sum of f of x means f and x are multiplied together. Here x is your midpoint values, and take the sum, and the sum would come out to be 3985.5, and then you need to take the sum of the frequencies. So because total observations are 100, so divide by 100, so you will get the representative number of cars in the order of 39.85, where most of the data is lying. So if you plot that histogram, which I plotted in the beginning in the title slide, that is representing the middle value of the data. So that represents the middle value data. Okay, and now we can move on to the many tab to do the same thing.